This is every day.
Wait. Today's the first time I started. Where it wasn't you
This is
started.
the first time you started today.
Today.
I believe you put me into the wall yesterday.
Yes, as you know, she's in Barcelona for Pharma, Europe. Tim, when you have a moment, I'd love to introduce your Bob.
based in Washington, D.C. Very happy to have with us Bob Mumgaard. He's the co-founder and CEO of Commonwealth Fusion Systems, also known as CFS, which is trying to build the world's first commercial fusion energy plant. Bob, welcome.
Thank you. Glad to be here.
And a little later today, you're going to walk up Broadway or take an Uber up Broadway to Columbia University for an energy conference there. So thanks for stopping by here first.
Glad to be here.
Wanted to start with something that's on everyone's mind, and that is the war in Iran. It's now in its beyond 50 days, and putting the future of oil and gas in question, whether it's always going to be reliable. So I was wondering, in the last 50 days, has your phone been ringing more with people interested in fusion?
I wouldn't say drastically more, and that's because it was already a lot of people interested in fusion for the same reason about energy security. If you think back, the war in Ukraine, of course, that's still going on, but the initial shock of that, pipelines were shut down, Europe didn't have energy, had to figure out and replumb the whole energy system, and that got people really thinking about, what is the reliability of energy sources that you depend on someone else? Same way that, like, today we question the reliability of energy sources that we depend on, like the weather. And it just raises the importance of having an energy source that really you can control, that doesn't have externalities. And fusion fits that bill quite nicely. And so that's been one of the reasons that people have been really interested in it and increasingly interested recently.
So you've been very consistent with saying that Commonwealth is going to get its first power from fusion in the early 2030s in a plant in Virginia. So, but help us understand, like, at what point does fusion, if it works, get to like 5% of U.S. energy, of electricity production?
So one of the, a couple things to remember. One, when you think about electricity is a giant market. So it is literally tens of thousands of power plants around the world that power electricity today, and we need to actually increase that by several fold when you look at the projections. So you're always talking about a giant market, and so replacing a significant fraction of that market is going to take time, no matter what energy source. One of the great things about fusion, though, is that it's the scaling of that, the time of the scaling, is not really dependent on, can you find the right geographies, or can you negotiate the right contracts, or the various flows of big systems. Instead, it's can you manufacture plants, and how fast can you manufacture plants and install them. And that has a big advantage because you can scale at the right demand. And when you go back and you look at the fastest we've ever changed out the energy system, when you think about France in the 50s with nuclear power just broadly in the 60s and 70s, that was really fast. And so if fusion can even approach that, it would be a big deal. But there's reasons to think it can go significantly faster than that. And there's some fusion proponents that think it can go, like as fast as some of the things we've seen in the digital world.
And you're competing at the same time with fission plants, which are different. They split atoms, and fusion is bringing them together. So how does what you're doing compare to the timeline for small modular nuclear reactors?
We think they're on similar timelines. They have different sort of barriers to how fast they might get there and how fast they might scale. But when you look and you see the small modular reactors, you start to see some of the first ones that are going to be built. They're just breaking ground right now. So designs are still in work. Things are still being through the regulatory process. A few of them just recently, like months, have gotten past the regulatory process. Supply chains are getting set up. That's not that dissimilar from fusion. You start to look at our plant in Virginia. You start to look at the supply chain that's been set up for our prototype plant, which is really one of the largest construction projects for a new energy source in the United States, even beyond some of the test reactors. And so we think that they're not on like that dissimilar timelines. They'll have different characteristics, though, because different dependencies on fuel, whether you have uranium or not, and where do you get that uranium. Also, different regulatory structures, very, very different in that respect. Different public acceptance criteria. So we think that they're not on wildly dissimilar starting times, and they could have different scaling rates.
So I'm still a little bit wondering when we're going to see more than the plant in Virginia. Like, that's going to take a while, early 2030s, and then what happens after that?
So, the first one in Virginia, that one, we've cited it. We've got partner in Dominion. We've got offtake, meaning selling the power to Google and E&I. So that one's starting to shape up. We intend to build multiple of that design. You want to have the supply chain and things set up. We're not yet announcing where we'll put other ones. We could put more on that same site in Virginia, actually. But we'll work on that over the next year or so. The goal will be to get going with the one in Virginia, and if capital's available, if the markets are right, start the next one shortly thereafter, and so that way you get the learning rates and you can learn as you go from one to the next to the next. And eventually you get to the point where you feel like you've got it really sorted out. The technology shown to work, the supply chain there, design refined to the point where you'd want to build them in parallel. And that would be the much bigger scaling phase.
Now, just a few weeks ago, you were appointed to the president's, it's called PCAST. It's the Council of Advisors for President Trump on science and technology. One of a baker's dozen, you're on there with just names that are household names. Sergey Brin, Lisa Su from AMD, Mark Zuckerberg. Like, were you surprised to be part of this 13?
I'm definitely honored to be part of it. I know what PCAST is as a scientist coming out of MIT, and I've had friends at MIT in the past who've served on it. I think it's an important position to be able to give advice on where science and technology is going. I was a little surprised at the list, because historically it's moved more in the sort of academic and science side, but I also think it's a very indicative list of where the big challenges are in science and technology. When you start to look at what the nation needs to think about in terms of energy, AI, quantum computing, these are the big challenges where technology, science, and business are all coming together today.
Mm-hmm. And you, so what does it mean for fusion in general to have, you were talking about how this PCAST is basically from the 1930s, got its origin. And now there's the first fusion person is on that. What does that mean in general for fusion?
It's a really good sign. It's showing the elevation of fusion. So fusion's moved from being really about the basic science to more applied science, to now we've got some demonstrations that we understand how the science works. And so it's at the stage of building the first power plants. And this is happening at the same time that we have a huge demand for energy. We also have rivals that are building advanced energy sources. You think about China and other nations who have said that they want to be first in fusion and are investing in large ways. You also have the emergence of the private industry. So, what are the policies and regulations that can enable that? So there's a lot of really meaty questions that are at this moment of change from science to the early power plant scale up. And I think it's good to be able to be a part of that. And it's been part of the administration's priorities. So they've said the top 3 priorities are nuclear fission, fusion, and AI.
And have you spoken with Trump about fusion?
I have not, no, but I've certainly, we're always been close to the administration, close to the Department of Energy. We came out of a Department of Energy funded lab, and that's historically where the foundations of the science have been. And so we definitely have, I think we're the largest recipient of Department of Energy funds of all the private fusion companies by quite a bit. And so I'm excited to see what the next generation of the public-private partnerships look like.
And you've been a part of a coalition of people wanting the federal government to put $10 billion, inject that in to U.S. fusion to develop it. Is that going to happen, the $10 billion?
we'll see what happens with the policy side, but there's certainly been a lot more discussion around what is the right number to do for such an important technology. And when you put it in context of particularly what's being spent overseas, we have a situation where the Chinese have outspent the United States somewhere between 3 and 5 to 1 over the last few years. You also have a situation where in the U.S., you have private investment that's at significant numbers now. It's more than that number. And so that's showing the interest at the commercial pull side. But we still have more to do on making sure that we can set up the right supply chains in advance, set up the engineering materials and things that we're going to need well in advance of needing them. And that's historically been the role of the Department of Energy. And when you think about the other programs that have been done for other energy sources, say advanced nuclear with small modular reactors, they have corresponding budget numbers.
So what specifically would the $10 billion solve for?
Yeah, so it really comes in three buckets. One bucket is to take the science labs, the national labs, universities, who are, have finished a lot of the science, but still have areas of material science and fusion-specific subsystems. And the National Academy of Sciences and other reports have put together, what test stands need to be done for those labs, those universities that would continue to build the foundations for all the fusion industry. That's like 1/3 of it. There's another third of it, which is really around commercialization. So building the first fusion power plants. And those fusion power plants, will not always be the best of the nth of a kind, the most economical. Historically, we've helped to get the first generation of power plants onto the grid with public-private partnerships. So those are sort of the two anchors, and in the middle is some translational research to be able to move from one to the next. Help basically take the lab innovations and put them into the supply chain and put them into the power plants.
And there are, of course, many hurdles. One of them being tritium, the supply of tritium. How will you get that?
So that's actually a common misconception. So fusion uses tritium, but it also makes it as it goes. So it's sort of like a sourdough starter. You use it and then regenerate it. And so that's been shown to work in various labs. And so to do it, you need a little bit of starter. And right now, that starter comes mostly from fission power plants. And so, for instance, Spark has tritium from that facility.
But at the same time, fusion plants are expected, there could be leaks of tritium, which is, it's radioactive. It only lasts for like 12 years, half-life, which is very, very short compared to fission reactors and the waste that they produce. But how do you deal with that problem, the potential leakage? And we're not talking about leakage into the water, but like actually through the walls of a fusion machine.
Yeah, so you actually capture that as you go. We have machines today that use tritium. National Lab in Livermore, Princeton has used it. We also have commercial exercises today that use tritium. And so it's well understood how to contain that, and it's actually well written into the regulations.
And going back to President Trump, the Trump family, Trump media, did a unusual investment last year. It's merging with TAE Fusion. What do you think that spells for fusion? These kind of public figure investment in fusion.
Now, on that deal, I'll let them speak more about that deal. I know that they're in I think a closing process. I do think it shows that just in general we're seeing more deals around fusion. Fusion being invested in by more institutional investors. You're starting to see larger and larger funds take over from what used to be angel investors. It shows a seriousness of the fusion as an enterprise, as a series of investments in the companies themselves, but also in the ecosystem. I think that's a healthy thing overall to have that happen. I also think it's a dynamic situation where you've got historically long fusion companies that have been around and working for a long time. They're looking for their next chapter. So you should expect to see some changes and some dynamism in the field, which shows, I think, a maturing of the overall sector.
And the Trump administration has made some interesting investments in Intel and also in companies that are producing minerals. What would happen if the administration came to you and said, hey, we want to take a stake in Commonwealth?
Well, it really depends on the details of these things. So this is clearly an administration that's thinking through a new approach to industrial policy. Historically, that's been mostly grants and mostly academic. And so having an approach that targets specific companies and helps them scale. Taking a stake in Intel came with significant capital to build a foundry in the United States. That's a strategic advantage. I think there's some interesting things to think about in that way for a new strategic energy source like fusion, but it would really depend on the details.
And Commonwealth has brought in $3 billion in private, which is the lead of fusion companies. But to get more, would you consider an IPO, or another company has done a SPAC, a Canadian company, General Fusion? That's, I think, closing later this year. What about those kinds of options?
Yeah, I think you really want to match the capital to what the job is at hand. And so we've been able to line up, a really deep private pool of investors, everything from Eni and a large Italian oil company, to Google and NVIDIA, to the private side of Fidelity and Temasek, the Singaporean Sovereign Wealth Fund, to hedge funds and university endowments. So we've built a broad and deep capital base, because we look and we see that in order to do a technology like this, you need to actually be able to go pretty long term. You need to be able to look out, 5+ years and have the capital to be able to build things. So fortunately, I think we're at a point now where you can actually build pretty deep private companies in deep tech. So think about SpaceX, had over 20 years to get to the point it is today in the private market, and think about Anthropic and OpenAI, similar timescales to us. So that looks pretty attractive. But over time, of course, the capital needs to build infrastructure go up. The existing infrastructure for electricity today is trillions and trillions of dollars, almost $100 trillion. So to gain access to that level of capital, eventually this ends up, tapping into probably public markets, but certainly infrastructure funding at the project level.
And at first, when we started hearing about fusion, there was a lot of talk about how it would help out with the climate change, curbing climate change. And now it seems to be like it's just feeding data centers and big tech and the world's demand for electricity. Where do you see it in terms of the fight to curb climate change?
I think the important part about fusion is that it's an energy source that doesn't have fuel going in or a smokestack coming out. Now that has two big impacts. One, smokestack, it means there's no emissions. So it is a great way on lowering emissions and cleaning up local environments, less local pollution. The other side of it is there's no dependencies on the stuff going in. So there's not a constraint there, no pipelines, there's no straits involved in fusion. And so you have different groups looking at fusion through their own lens, but at the heart of it, it's all the same, which is the world's going to need a lot of energy, probably in electricity. That's the highest form of energy. We want to be able to build that fast wherever we need it and operate it whenever without externalities. And that really is the package that fusion brings. And so I always caution people to don't look at fusion as only defined by your viewpoint. It actually fits multiple goals.
You mentioned China, and there seems to be, in the media you'll read about this race, and it seems to be like, winner takes all kind of thing shaping up. And it doesn't seem like there's, at this point, collaboration between China and the U.S. on fusion, except for at this massive project in France called ITER that is now quite a bit delayed. It's coming on later. What do you make of the U.S.-China race? I mean, is there any room to work there, or is it that's kind of off limits?
Actually, historically, there was quite a lot of cooperation. So if you go back 10 years ago, actually the Department of Energy had a policy that we were shutting down U.S. facilities, including one at MIT and a couple others that we just decided not to build because the Chinese were building their facilities, and we actually sent people to go help them bring the current generation of Chinese facilities online. Of course, that policy was at a different era, and now when you look at the sort of the different directions that China and the U.S. are going, and some of the tools they're using in that competition, it's pretty untenable actually to have cooperation in something as fundamental as fusion. And so we're starting to see that, and we've seen that basically firewall go up. First starting with the government policy and now moving into the other sectors, including supply chains, et cetera.
And what if China wins the race, so to speak? Why would that put the U.S. at such a disadvantage?
Access to large amounts of energy, that is a strategic advantage to be able to build other things. So, if you need to have a lot of AI, or if you have AI without the greatest chips and they are very energy inefficient, having large amounts of energy can actually help you get around that. To be able to industrialize and power things, to be able to grow the economy. There's basically a direct correlation between energy and GDP. So having a new fuel for that and fusion will have large ramifications, just even domestically inside China. Then when you think about the people that are making decisions, countries making decisions about which system to more closely align with, having the ability to export fusion to those places, that could be an important piece in the basket of goods.
Now let's go to Virginia, where you're building this plant. Construction, you've said will be 2026 or 2027?
We're not quite sure yet. Our goal is to be able to have it as early as late 26. We're in the permitting process right now. We actually received several of the important permits. We still have a couple more on the electricity side. As people know, that permitting for the grid is a long lead time item, so we're in that process now. But the goal is to be able to line that up so that as soon as capital is available, we can actually go build that project. And so we're also at the same time putting together the capital coalition to go do that. And the sequence for the company is we've got the large project in Massachusetts, which is the demonstrator, the last demonstrator. It'll get more power out than in, called Spark. That's well under construction. It's over 75% complete. That'll turn on here in 27, and then immediately go as fast as we can to construction of the first commercial power plant in Virginia. And
going back to 2022, there was this huge announcement from the Lawrence Livermore National Lab. Big media spreads. There were people talking about more energy coming out of the reaction that went into it, and then they replicated that a few times. But really, there hasn't been front page headline beyond maybe this Trump media merger. What do you think the next 2022 is?
Yeah, so it's definitely Spark. So in Massachusetts, that facility, is one of the only. It's really the only one under construction that is going to really push the absolute bleeding edge of the fusion engineering and the science forward, and it's going to do it to the commercial relevant scale, commercial relevant amount of power and performance. And so, we had started building that in 2020. Started the early work and really got started in construction in 21, 22. Because we could see that the National Ignition Facility in California was on track to ignite. It was a question of when exactly it was going to happen, but the right things were there, and the models, the big supercomputer simulations were showing that they were closing in on it. And so they did that, and that was great because it showed that the understanding of the science works the way that everyone expected, that we can actually tune it up. It's a very different platform than a power plant, different reasons to build that. But that science at the heart of it is the same science at the heart of the plasma physics inside our machines. And so that was very, very welcomed. It says that we're on the right track to be able to take that and make it into a much more powerful system and a much more commercially relevant package. And so that'll be Spark, starting to turn that on in 27.
Now, this month there was an article in Nature Energy, the science magazine, and they brought up a lot of questions. They said that the projections are too optimistic. They said the two different designs, like using magnets, which is what Commonwealth is doing, and lasers in the California. Those designs aren't there yet. It's too optimistic, and the learning curve is not as great as companies have said. What's your reaction to that?
That was from a group that is really unaffiliated with fusion, and they didn't really call anyone that we knew, and certainly no one that is building anything. So it was an interesting academic view, similar to things I've read in the past about. Oh, we can't build AI very fast. It's not gonna get anywhere, or we can't make going all the way back to biotech. We're not gonna be able to scale that. There's always gonna be people that say something like isn't gonna go as fast as you want. But when you actually look at the fundamental pieces of it, the speed at which we're able to build our things, the ability that we've actually shown to decrease the cost of every component that goes in it, those are following well-known industrial trends that are, not from the 1950s and 60s, but are from today. And so, we remain very bullish. And furthermore, like national policy in Japan, Korea, the Germany is actually also counter to that paper.
And just wanted to try again. Like, when is the average? I mean, is it going to be in Virginia that all of a sudden suburbs and cities are going to be getting fusion power in like the 2040s? When can people actually see that it's happening?
Yeah, well, I mean, in the early 2030s, power bill in Virginia is going to have fusion electricity in it, and then our hope is by the middle of the 30s, you have several power plants up, and then you're really hitting the gas pedal at that point. And
where are you looking outside the U.S.?
Well, certainly markets are interested in the UK, who has a very forward-leaning fusion policy, Germany, Italy, and then there's places that really need fusion. So when you think about the amount of land it uses or natural resources that it doesn't consume, places like Japan and Korea, Singapore are areas where they can look and see to run a modern industrial society without dependent on LNG going through tankers, or without depending on uranium, plutonium, and weapons complex adjacencies. Fusion really fits their long-term growth trajectory, and so that's why you see them investing. So those are interesting markets.
And to get to those other plants beyond Virginia, how much more private investment do you need from folks?
Well, eventually it becomes, with a proven power plant, it becomes something that looks like building any other power plant. I think that's one of the cool things about fusion and infrastructure is once you prove the model, the next stage of scaling it is actually something the world has already done. Like, there's tens of thousands of power plants, and the world built them. And they'll have to replace them, and so replace them with fusion. If that's the lowest cost, lowest impact option, that's the goal to get to. And I think that we could actually see that happen quite rapidly when you start to map out how the footprint is of capital. Capital exists. Supply chain. There's not a lot of specialized atoms you have to dig up or find, and then the manufacturing capabilities. So from a private capital side, it'll take capital to get the first plants proven, and that'll come, we think, from private markets, but hopefully also help from government, help from the users of electricity that comes from fusion. But then after that, it actually looks like businesses that we've been running since Thomas Edison built the first power plant here in New York.
And talking about Virginia, that is quite close to the sort of the Rust Belt of the U.S. And you talk about electric plants that are closing, like coal plants. Are you already searching out places that your fusion machines could go, because the water is there, the electric system is right there?
Yeah, certainly, and a big impacts that we look for are places that already had power plants, because that means the electrical system's there, it means the workforce is there, they understand what energy brings to the community, and it also means that they understand the downsides of existing energy sources, and so they're much more interested in what fusion lacks in terms of pollution and fuel coming in and out and emissions.
And has that outreach already started to those communities?
Yeah, we have a robust and have had a robust ground game of looking at sites, and the Virginia site was actually came out of a search across the nation. There was about a dozen sites that we looked at seriously, and some of those are sites that we still have in thinking about what the right sequence is.
What other kind of sites are interesting?
Industrial sites are interesting. Power plant sites are interesting. Some that are greenfield, where you don't have as many constraints with fusion. So, for instance, water, you don't have to be near a big waterway for cooling, things like that.
What parts of the country are?
No, it's really all over. You think about the reindustrialization, places that need a lot of energy. So that could be in the Rust Belt, some places in the West.
Very good. Bob Mumgaard, thanks for joining us.
Thank you.